Welcome to you all for the second day of today's webinar. Good morning to all participants, resource persons and members of organizing committee. Namaskar. I myself, Sri Prasanta Kumar Jana, reader in mathematics, have the pleasure and privilege to welcome you for all joining today's international webinar on application of mathematics in science and technology, organized by Mathematics Department of Salepur Autonomous College, Salepur, under the aegis of DBT Star College scheme. Thank you all for joining with us. Now, I request our principal companion of this webinar, Professor Dr. Umesh Chandra Patisar, to deliver his welcome speech. Over to Principal Sir.
Thank you. Thank you, Professor Prasanta of our college. I welcome again all the participants. Good morning to you all. As it has been highlighted, this is the second day of the international webinar being organized by the Department of Mathematics of our college. This is under the aegis of the Star College program. Should I add here that our college has been included in the Star College scheme selected by the Government of India, Department of Biotechnology, Physics, Chemistry, Mathematics, Botany and Zoology. These 5 departments have been included to develop academics, teaching, learning and research with regard to the program being included in the Star College scheme. And this 2 days international webinar is only to clear all the doubts related with different mathematical analysis, as you have heard from the title of this particular webinar. I extend a very warm welcome to all the participants and my profound regards to the resource persons who happens to be the domicile of Odisha. So we have the first speaker, Dr. Sridhar Nayak, is the Associate Professor, Disaster Prevention Research Institute, Kyoto University, Japan. He will talk on introduction to numerical modeling of climatic problems. So it is the byproduct of research because we are able to know regarding various type of natural calamities which have very recently happened in India, and these are all dependent on the mathematical modeling. I being the person from economics background, we also use the mathematics modeling to justify different hypotheses. In Japan, we have heard in our age of childhood the concept of a number of earthquakes which have happened, and now the research is on that particular aspect, and I hope that his deliberation on numerical modeling of climate problems will be helpful to clear many doubts which are there in the minds of we intelligent people also. We will able to know regarding the causes of the Phani, Titli, Amphan and various type of natural calamities which have happened in case of our country, our state Odisha, and it will help also to protect the humanity from different type of disaster. So I welcome you, sir, Dr. Sridhar Nayak. Our next speaker, Dr. Devashish Pradhan, is the Assistant Professor, Defense Institute of Advanced Technology, Pune. He will talk on mathematics in image processing. So this is how mathematics is useful for humanity to protect lives and also to protect the livelihood. In the present context, with lot of climatic changes and changes in the international relations also, because we are talking with regard to the concept of your international relations, and in this case the mathematical modeling is imperative to draw valid conclusions, and it will enable the policymakers also to take right decisions. So very nice of you, sir, for accepting our request. Our college, as you know, that 56 years old college, multi-faculty co-education college with art, science and commerce, and teachers, the students, they are working hard also for the last 9 months, even during the period of the pandemic, to maintain the tempo of academics through webinar. Now we are in touch with you, or we have got you only by the COVID pandemic. Unless COVID is there, then we all organize the seminars that is in the physical form, in the offline mode, and it is very difficult to get you as the research person and to listen from you. So I again welcome you as you have accepted our request, and we are working hard to sensitize the people, to enlighten people, and to focus on the new ideas. I again invite you, Dr. Sridhar Nayak and also Dr. Devashish Pradhan to physically come to our college whenever you are coming to Odisha. Let us improve our relation. Let us have relation with our college. Though this is a small college, but the faculty, the students are very sincere and disciplined. And we hope that your academic achievements will enlighten our students and also our staff members. I again invite you to Salehpur Autonomous College, sir, whenever you are coming to Odisha, because we have Rasgola. You know, Vikrantagar Rasgola is there in Salehpur, though we have unofficially GI tag with regard to Rasgola. So we be very good host to you. And I hope that you will accept our invitation whenever coming to Odisha. And I hope that our college is very good. And I hope that you will be more and more happy by being in touch with us. Thank you. Thank you all.
Thank you, sir, for your welcome address to our participants and resource persons on this webinar. I, on behalf of Mathematics Department, extend my deep sense of gratitude to you, sir, for your presence in this webinar, in spite of your pressing engagements in office. Thank you, sir. Now, I request our head of the department, Dr. Sangeeta Mishra, madam, to introduce the learned resource person of this session, Dr. Sridhar Naik, Associate Professor, Quetta University, Japan. Over to Madam Dr. Mishra.
Thank you, sir. Good morning, everyone. Esteemed patron of this webinar, Dr. Umesh Chandrapati, Principal, Salehpur Autonomous College. The respected resource person, the members of this organizing committee, our web designer, Sri Asian Patnaik, and my dear participants. First of all, I welcome everyone to the second day of this webinar on the topic Application of Mathematics in Science and Technology, organized by the Department of Mathematics, Salehpur Autonomous College, under the aegis of DBT Star College Scheme. Our today's resource persons are Dr. Sridhar Naik, Associate Professor, Disaster Prevention Research Institute, Kyoto University, Japan, and Dr. Devashish Pradhan, Assistant Professor, Defense Institute of Applied Science, Girinagar, Pune. I, on the behalf of the department, express my wholehearted thanks to our resource person for accepting our invitation for this webinar. It is a great honor for me to introduce a resource person of this session, Dr. Sridhar Naik, who will deliver on the topic Introduction to Numerical Modeling of Climate Problems. Dr. Sridhar Naik is presently working as a program-specific associate professor in Disaster Prevention Research Institute, Kyoto University, Japan. He had joined the institute in 2017. Prior to that, he was a researcher in NIED, Japan, from 2014 to 2017. Dr. Naik is originally from Odisha, where he studied up to his master's degree. He was BSc Honours topper in mathematics from FF University. He did his PhD from IIT Kharagpur in the year 2014. He has qualified the GATE exam in mathematics, and Dr. Naik also was the holder of many scholarships, is holder of Ministry of Human Research and Development Scholarship received from IIT Kharagpur, India. Selected for getting scholarship from Austrian Academy of Sciences and for RICAM, Austria. He was awarded with a Young Talent Researcher Level A CNPQ, Government of Virgil. He got many more funding from Kyoto University, Japan and NIT, Japan. He is an active member of Japan Society for Civil Engineering, Japan Society of Hydrology and Water Resources, Meteorological Society of Japan, Japan Geophysical University, American Geophysical University, Asian Oceania Geosciences Society. During this excellent career, he has involved in many sponsored projects from Government of India and Government of Japan. He has so far 35 publications in national and international journals. He has also participated and presented paper in 70 conferences held in different countries. He had visited many countries several times, such as USA, Europe, Singapore, as chief speaker and guest lecturer. His present research focuses on climate modeling, specifically on the dynamical characteristics of various extremely heavy rainfall events and tropical cyclones in present climate conditions and with future global warming conditions. I sincerely hope his vast knowledge and research experience will definitely enlighten our today's webinar and participants. I request Dr. Alok Mahanti to brief the topic, and now over to Mahanti.
Hello, good morning. Now this is the time for highlighting the today's topic to be presented by the versatile, profound and elegant researcher come Professor Dr. Sridhar Naik from Kyoto University, Japan. Before listening to Sridhar sir, I have the opportunity to brief this topic. The climate models used by the scientists today rely on some of the world's most advanced supercomputers. However, less than a century ago, climate models were little more than an idea about the basic equation roughly sketched out on paper. After the Second World War, US had quickened the pace of development of climate models dramatically. In the late 1960s, policymakers were being presented with the model's findings, which strongly reinforced the theory that the continued rise in the human-caused greenhouse gas emission would alter the global in profound ways. When creating climate models, scientists use one of the three common types simple climate models. One is energy balance model, EBMs. Second one is intermediate complexity model. Third one is general circulation models. The earliest and most basic numerical climatic model are EBMS. EBMS do not simulate the climate, but instead consider the balance between the energy entering the Earth atmosphere from the sun and the heat released back out to the space. A step along from EBMS are radiative, convective models which simulate the transfer of energy through the height of atmosphere. For example, by convection, as warm air rises, radiative convective models can circulate the temperature and humidity of the different layers of atmosphere. These models are typically one dimensional, that is only considering energy transport up to through the atmosphere, but they can also be 2D. The next level of our general circulation models are called as global climate models, which simulate the physics of the climate itself. This means they capture the flow of air and water in the atmosphere or the oceans, as well as the transfer of heat over the period. Scientists have gradually added in other aspects of the Earth system to this GCM. These would have once been simulated in standalone models like land hydrology, sea ice, and land ice. There are also regional climate models which do a similar job as GCMs, but for a limited geographical area of the Earth. Because they cover a smaller area, RCMS can generally be run more quickly and at a higher resolution than GCMS. A model with a high resolution has smaller grid cells and therefore can produce climate information in greater detail for a specific area. Finally, climate models are probabilistic, indicating areas with high chances to be the warmer or cooler and wetter or drier than unusual. But our reverse learning resource person, Dr. Sridhar Naik sir, has focused on the RCM system over India, especially northern, western, southern and northern eastern regions over a 30 years long climate simulation toward the Indian temperature and participation climatology. So this is a time to hear from you, sir. Thank you to all. Over to
Hello. Good afternoon, everybody. Oh, sorry, it is morning there. Here it is afternoon.
Thank
Anyway.
you, sir, for highlighting the topic to our participants. Now, I request Dr. Sridhar Naik sir to elaborate and present the topic to our participants. Welcome to Sridhar Naik sir. Over to Sridhar sir. Feedback link will be given after the second session.
Okay, good morning to everyone. Before I start my presentation, I would like to ask you a few questions. Am I audible to you clearly? Am I audible to you clearly?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes,
Can
sir.
you see my presentation also?
Yes, sir.
Okay, nice.
Yes, sir. Visible, sir.
Yes, sir. Visible.
Okay, thank you for confirmation. Okay, first of all, I would like to heartily thank to Alok sir for introducing me everything and bringing me here. I would like to thank Prashant sir for organizing this event, and special thanks to Umesh sir. Well, very good welcome and inviting me physically, at least to have the Rasagulla, Salepur Rasagulla. Yeah, I heard and I have taken many times there while in India. And also I would like to thank to Sangeeta madam for the nice introduction about me. So now it is time of the presentation of my presentation. So today I will discuss about an introduction to the numerical modeling of climate models. I will not discuss about the introduction mostly, but I will speak some research as well as some introductory things so that I hope everyone can enjoy my presentation. So before going into the detailed presentation, I would like to first, I will first discuss what is climate, then what is climate problems, then how do we model all these problems. So slowly I will go one by one slide. So I hope everyone can understand easily. So first, what is climate? Before going to climate, we should understand what is weather. Everyone know what is weather. If we define it, it is actually a state of atmosphere at a particular location. For example, today's temperature is 20 degree at some place, maybe Kottagar, Bhubaneswar, somewhere. Or we sometimes call it is humid today, or we call sometimes today is a rainy day. So this kind of statements we say it is actually it is some state, a particular state of atmosphere at a particular location. So we call it is weather. So now if I tell it is what is climate, then we need to take average of this state of atmosphere for at least 30 years. So it is like that. So climate is actually an average of weather, which is generally about 30 years over a region. So now you may ask me why it is location and why it is region. I will go in the next slide. So we mostly say climate over a region like this. Temperature over Odisha, it is about some degree temperature, some degree Celsius. Odisha is warm in summer and it is wet in monsoon season, which we call rainy season. So now you may ask, now I hope you understood what is weather and what is climate. Now I will tell you why weather we call in a location but climate in a region. So mostly weather we call, you may understand here, look what is location and region. Location means sometimes, for example, we call a local. It is local and it is regional, sometimes regional manager. It means if you consider in bank, you can understand regional manager means it is over a region. It means it considers many places, and a region head we call regional manager, something like that. A location is a particular local region. So if you see the example, we can see like this. Suppose temperature in, if I take temperature over a certain place, so for example Soro and Baleshwar and Bhadrak, and if I measure the temperature for 1 year, every day up to 30 years, it is 30 years day. So you will see like these temperatures, suppose at Soro, Baleshwar and Bhadrak, and if you see the temperature magnitude, you see on day 1 it may be similar 20, 21 and 22 degree, but if you see the 22 degree in day 2, 25 degree and 22 degree 24, it's also mostly similar. But if you see, for example, you see this one, day 3, it is 25 degree in one place, but in Baleshwar it is 31 degree. It means in Baleshwar it is warmer than Soro or Bhadrak. It is cool. It is compared to on day 3, compared to Baleshwar, compared to Bhadrak, the Baleshwar temperature is higher. So temperature varies in every places in every time. But if I take a 30 years average, you see it is 30 years average from day 1 to 30 years day. In each place, you see temperature mostly similar. It is about 24 point something, 24 point something, 24 point something. So now you can imagine all the places temperature is mostly similar in a climate scale. So we don't tell that climate at Soro is 24 point something, at Baleshwar 24 something. So we call it, if you see it, if I take it over a region like Odisha, some place, so we call it in Odisha temperature 24 degree something. We tell like that. That is why climate we call it is a region, and weather we call a local. Similar in rainfall also. I don't want to explain this. So similar case you find if we take the rainfall cases also. But one thing you can see, in climatic scale, the rainfall amount is similar if you see at all the places. Not all places in this example. But if you see some particular values, you see here in Baleshwar it is 16 centimeter rainfall on day 2, but in Soro there is no rain. So now imagine if this kind, so now imagine this is called a weather event, because when I talk about on this day basis at each place, it will be weather. But this, when I take average, this is climate. Now I assume you understand what is climate and weather and how they're different. They are different. So now you imagine on this day, on these values, you just imagine you just these values 12, 16, 15, these values. These are most extreme cases, we call extreme cases. And on these cases, we mostly experience some kind of extreme rainfalls like flood or flash flood or very heavy rainfall over that place, so that we care about these things, because these kind of events mostly mostly damages a lot. You know, sometimes the water flows on the roads and enters the houses. People's don't transport easily, and they can't commute to hospital and all these things. You have also experienced, sometimes you might have understood these things. So we mostly care this kind of events nowadays, because this kind of events are mostly damaged, as I told. So now I will not discuss much on this. So next I would like to discuss what is the climate problems actually. What is the climate problems? Yeah. So we all understood that, we are experiencing that the climate changing are taking place. Climates are changing, you know, and also it will also go on happening in the future. We cannot stop the climate change. It will go on because our earth is rotating, and because if you go to physics part, you can see the earth is always rotating. So it is, and also for which we are getting our atmosphere is always in motion. You know, the wind or the pressure and everything are changing at all places. So, and also in certain periods, what will happen, everything is going smoothly, but in certain periods what happen, the climate conditions change so dramatically that they cause problems in human life, and as a consequence we face a lot of droughts or floods at many places. And we know the human activities also has become a significant factor in the climate system. For example, because of the human activities nowadays, now in recent years, the greenhouse gases in the atmosphere, the concentration of the greenhouse gas has been increased. As a result, the global temperature is increased. If the temperature will increase, we know there is a theorem, that Clausius-Clapeyron equation. In physics, we have heard about it. According to the Clausius-Clapeyron equation, I may show you later. I don't know whether I kept that slide. Anyway, so if the temperature will increase, according to the Clausius-Clapeyron equation, then the moisture holding capacity in the atmosphere will increase. You know, it is about 7% per degree rise in temperature. So if the moisture in the atmosphere will increase, then it is obvious to expect some more rainfall. So ultimately it become, if temperature will increase, then we will get more rainfall. So if more rainfall will occur, then it is sometimes we may get that kind of heavy rainfalls, which floods and something. So keeping on these things, the temperature will increase in future. We mostly predict, we are interested to see what will happen in our future. So for which we need the climate models for the development of the societies around the world. Why we necessitate the climate models, and why do we present? We want to prevent the global and regional climatic and environmental disasters. The disasters, not only the floods, but also the intensity of cyclones or intensity of the floods, because nowadays floods are maybe less intense. It is giving less rainfall. You may tell that, yeah, it's not a problem, because someday one day it will, the water maybe drain in one day. But in future, we are expecting nowadays the water, the rain getting from the flood events, which is drained in one day. If the similar situation, if the similar infrastructure will stay in future, then the rainfall will get in future floods. Maybe that rain water will block the road minimum 3 days, 4 days in future. That's why we are very careful. And also, if you compare the cyclones, in previous years, cyclone and the recent year cyclones are, if you compare, the recent days cyclones are more intense. They bring more heavy wind to destroy our infrastructures and hamper the human lives. So this is what the climate problems. So now, how do we model this kind of problems, and how do we do model the climate to mostly to prevent the global and regional climatic and environmental disasters. So I will show you. So before showing that, I would like to also highlight some climate problems. You can see some real scenarios. It is not only in India but also in all over the world. You can see here is an example for Japan. You see in just in 4 hours, there is a heavy rainfall which is 15.6 inches. You see the scenario. It is on 5th 2000 on July 5th 2017. This case happened, and this is in Japan. If you see this is in New York. It is also in May in 2017, in May 2016 it is in New York in USA, and also in India. If you see, it is in 2018 in May. You see, it is in Mumbai case. I think it's clearly written that greenhouse gas emissions cause this extreme heavy rainfalls in India. So all these things, you can see that these are the climate, mostly the climate problems, not only the floods, but also sometimes the droughts. Sometimes what happens, and because of more temperature, the some places like our desert regions, we are not getting rainfall because all the evaporation, all the waters in the ground surface goes up, and because of the temperature increase, the moisture, whatever on that place, and they can't. It is mostly dried. That's why there is not much available of moisture in the atmosphere, and they can't produce the rainfall, and that becoming droughts. If the droughts happen in more years, then you know what will happen. And similarly, another climate event as I highlighted, that is the tropical cyclones. That in Odisha we are experiencing a lot of cyclones, we know, every year. And nowadays the number of cyclone events are increasing. You know, the 1999, yes, super cyclone. After that, if you see the statistics, after 1999 cyclone, super cyclone, we experienced similar cyclones in 2012, I think, Hudud. Before that, in that 12 years, there is not much number of big cyclones. But after 2012, you see Hudud, Thailand, and one more I have not remember, and recent one also. So you see how many cyclones are coming in recent years. So the number of it means the number of extreme events are increasing in recent years. That's why we are careful to all these things. So we worked over Japan to see what will the extreme precipitations because of the temperature increase over Japan in future climate. We use many regional climate models to understand the future scenario of extreme precipitation events in future because of the temperature, and we published this paper in Climate Dynamics. So we have considered many models, if you see, and I don't want to explain everything in detail, but I will tell you just this one. This is the down one. All the models are highlighted here one by one, and here the dot line is you just look into the solid line and the dot line, the deep one, the red color. The dot line is the precipitation. Okay, first of all, let me see what is y-axis and what is x-axis. X-axis is the temperature, and y-axis is the precipitation intensity. So if you see this graph, you can tell easily that the precipitation increases with temperature. You see, temperature with temperature. So I will not tell what is here, but it increases with temperature. You see, it is increasing with temperature. And the dotted line are according to the Clausius-Clapeyron equation. If temperature will increase, then what will happen to precipitation? So now you see the dotted line is for present climate, and the solid line is for the future climate. Now you can see the precipitation intensity for present climate and future climate for lower temperature are okay. You see up to 20 degrees centigrade is okay. But after the temperature got increased, you see at the higher temperatures, which are now we are experiencing, temperature getting increased. So if temperature getting increased, you see the extreme rainfall intensity increased. You see, it is about 20 to 40 millimeter per day. So we care about these things. So in future climate, if you see all the, this is different GCMs, this is this GCMs. There's, yeah, I'm very much thankful to Alok sir. He explained what GCM, RCMs, and the older version of regional climate, older version of the climate model. I'm very thankful to him that he made easy of my easy of my presentation. So if you see GCMs and this is GCMs, this is GCMs, this is GCMs, and this is RCMs. So means, you see, this is GCMs. For here all the different kind of GCMs and RCMs. Sometimes we have used some kind of GCM output in RCM. So this is different topic. So I don't want to go on that. So you just see, imagine in all model simulations, you see the future climate is the solid one, the present climate is the dotted one. You see everywhere it is increased. Everywhere it is showing in future climate and higher temperature, the precipitation intensity will increase. So it means we will experience whatever event will occur, the cyclone or flood, but the intensity will increase. It means it will bring more rainfall. So if it will bring more rainfall, what will happen? You can imagine now. So this is what the case. This is the scenario of Japan. So I also studied similar thing over India. Also, I found similar situation. So now I will discuss what is model. So how do we model all these things? So here I have very less time. I cannot explain everything in the model, but I will just give you simple understanding what is actually a model and how the model works actually. So what is the model? So if I will ask in a layman, means what is educated or uneducated, and he doesn't know anything, what is model? So in the present scenario, you will just sometimes people tell like this, say, yeah, the film stars are the models because we mostly follow them. Many people follow them; they are models. They tell that. And some people tell the post stars are model. They are the models. And some people sometimes, if we will go to the higher education things, then people tell maybe yes, these are the models. These are house things, or these cars are different car, or these different vehicles are models. So now you imagine what is the model and which are models and which are not models. So for some people, these film stars and sports stars are model. For some people, no, these things are model. But in education, if you see, these are not models. These people are not models, but these are the models. So if I remove those two things, so now I'll tell you why we call these things are models. Now you imagine why. Because actually we define a model is a simple representation of a reality that helps us to understand how something works. You see, if I show you this house, I will give you this design of a house. You can build a big house. Just I'll show you this one. My house should look like this so that you can build a big house. It means it's just a representation of a bigger thing with a smaller thing. That is, it represents a reality. So I hope you understood now. Similarly, in the car, you just see this small image, you can see how the car looks. It means it represents a reality. How the bigger car or the car you are using, how it looks. So now you imagine why we call these things model and why we don't tell the model just a person. So now if I define it in climate case, so what is a climate model? Similarly, I will tell, like here I call it's just simple representation of reality. Similarly, the climate, I will show you some image or whatever that should represent some real scenarios of the climate. It looks like that. So the climate model will be a mathematical representation of the physical processes that determine the climate. It means it shows whatever I will show you in mathematically or in graphically or whatever, that shows some reality of the climate things. And this climate model mostly use mathematical models, mathematical equations to characterize how energy and matter interact in different parts of the ocean, atmosphere, and the land. Because our Earth has these mostly three components: the ocean, and the atmosphere and land. And all the climate models are very complex to understand because they deal with huge quantity of data, and also they require very large number of calculations. We can't do it in a simple calculator or computer. We need supercomputers, which is equivalent more than at least 100 number of similar one computer, 100 number of computers. If we use 100 number of computers at one time, it may be a small supercomputer. So now I'll tell you how different steps, how we model the climate. So the step one, this is the 3 steps. So the first step is we first develop an understanding of the physical system of our climate. So I will not explain everything, but you know all these things. See? So we first understand how the physical system works. You know all these things, which we call the various components of the climate models. This is solar radiation. You know how the solar radiation occurs and how it comes to the Earth and how it goes. Some solar radiation is observed by our Earth and some goes back. And whatever observed in our Earth in the night time, again they goes back to the atmosphere. You know all these mechanisms, so I will not discuss, but all these things is considered. So this is actually different components, various components. So this is solar radiation. If you see, radiation occurs where, and the dynamics. So I don't want to go to all the details. Surface processes, the various ice, snow, vegetation, albedo, moisture interchanges occurs in our atmosphere and the land and the ocean everywhere. So all these things, and chemistry also, various natural gases and all. And so first we develop an understanding how the physical system works what is the physical system and how it works in all these compartments, ocean, atmosphere and land. Then we translate this physics to understand this physics which describe our understanding into a mathematical system. It just looks like this. We know all these laws of the fundamental law, which we call the fundamental laws in the model. So we know all these things. Conservation of energy, which is first laws of thermodynamics we use here. In physics, we know what happens if we increase the energy or if we give some energy, what will happen? It will increase the internal energy and it will make some work done. And the conservation of momentum, conservation of mass, and an ideal gas law. So we mostly translate what happens in all these cases, in all these various components in our system. Different laws, you know these things. So now what happens? Now what we do? If after translating all these things, and if I use these equations, right, one by one, conservation of energy, conservation of momentum, and conservation of mass, and ideal gas law, I will not derive here how we find the equations of all these laws. All these things you can see in textbook, and you have read all these things in physics. So if I translate these laws, ultimately it will become a system of equations. It is just like this. So if the conservation of momentum, I told you, if you derive, you will find this similar kind of west wind, south wind, vertical wind, and conservation of mass, this is the equation. Conservation of energy, this is the equation. Conservation of moisture, this equation. Equation of the state. So all these equations, now imagine all these equations. So these are the equations actually. How many equations for the conservation of momentum? I got 3 equations: west wind, south wind, vertical wind. You know west wind, what is west wind, south wind. From westward, the wind comes from west to east, south from north to south, and the vertical wind is the vertical direction. So the 3 wind equations. Conservation of mass, 1 equation. Conservation of energy, 1 equation. Conservation of moisture, 1 equation. And equation of state, 1 equation. So total 7 equations. Now, these 7 equations mostly govern the atmosphere. All these laws, if I write in equation form, I will get these 7 equations. And all these 7 equations mostly govern the atmosphere. And this, as I showed you, it is a set of 7 equations with 7 unknowns. Which are the unknowns? The wind, west wind, south wind, vertical wind, which is called UVW, and the pressure P, and here we call here the pressure P, and the temperature T, and specific humidity Q, and the density. Total 7. So here I have 7 equations. You see 7 equations and 7 unknowns. These are the unknowns: UVW, P, T, Q, and density rho. So from all these 7 equations, and we have 7 equations. Now imagine, now in mathematical way, we have 7 unknowns and 7 equations. Now you can solve it easily because it is just in mathematics. In mathematics, if I give you 7 equations and 7 unknowns, you can tell, yes, I can solve it. But the problem is, all these equations are non-linear, partial differential equations. So it is very difficult to solve mathematically. That is why we use numerical methods with some finite time steps and grid boxes. How many times I have left? 5 minutes more? 10 minutes?
Sir, 15 minutes, sir.
Okay, 15 minutes, a lot of time. Okay, thank you. So then it's fine. So now you see we have 7 unknowns and 7 equations, and all are nonlinear partial differential equations. We cannot solve it analytically, in mathematical way. So we use numerical way, and we use some finite time steps. How we do it in finite time steps and grid boxes, I'm just show you right now. So now you see some marks in the screen. I don't know why I see many marks in my screen. Anyway, so suppose it is India. You see it is India, and how can I start explaining? Okay. So suppose I am taking in a region, and I put it like, and I make a grid box, different grid boxes. I make it you just see how I represent this India. You can see here the India, and I just make a grid mesh. You see the mesh, I put it, and I have put different just make it blocks, different blocks. You see this, the black dots, these cross points are actually the data points are here. You can see. I will not go into much details. Just for understanding, I'm telling you, to run the climate model, we need some input data. Without input data, we cannot do anything. At least we need some inputs. Inputs means that some informations, like at some places we should have some information. Suppose at plus I have some temperature data set, humidity or wind, whatever. I should have some information. Otherwise, I can't do anything. Model has nothing. Model doesn't know anything. Whatever information we will give, and that will give you the results. And model, what you do, the model actually solve that 7 equations. What I showed you, the nonlinear partial differential equations. Model solve that equations. How it is solved? We have 7 unknowns and we have 7 equations. So now how it will solve? I am going that. So we have some. First, I represent this region. This is suppose India. I represent this region into different grid boxes. You see different grid finite. You see the finite grid boxes. You see the grid boxes. So now I have information in these boxes. You just plot. You just take any one block. You can see. Just take, suppose this one I am taking. Suppose this one. In this grid blocks, we have four values at each point. So now I have 7 equations and I have 7 boundary values, I can tell now. So now it will become a boundary value problem because I have values at the boundaries and I have 7 unknowns. So it will become a boundary value problems. So now we can solve it if in numerical way. So how I do this, I will show you. So now if you take these 4 boundaries, you see how complex the model is first. So if I take this 4 boundary, you imagine, you say how big place this is. And from here to here, it is about 1,500 kilometers. You see, from here to here, it is about 1,500 kilometers. And from this to here, it will be about 800 kilometer. In the 800 kilometer, if I give you just temperature here and here, can you calculate the temperature? What will happen everywhere? It is quite not impossible, but it's quite difficult, because there is lot of variations, like in mountains, some high hills, and some deserts, some rainforest. Many things will be inside. So it is really difficult to understand the climate system. So everything we do in regional climate model, it will just give you this kind of values, but a global climate model will give you this kind of information. But in regional climate model, will take all these informations to give you the more accurate values. So if I take this one, you see what is there actually. Sorry, I'm showing here anyway. If you see this one, it's a place, you see, I have just in a bigger size. If you see, it looks like this. Some places I will take also consider the atmosphere, because atmosphere takes has a very vital role of everything. So it looks like this. I just took one thing, and in this atmosphere also there are many things. You see, there are many things. We land, it's a land and atmosphere, and the solar radiation is coming and it's going back, and the chemistry also, there are many gases. So there are many things are in here. So it really looks like this. If I take this one grid box, it looks like this, because I will make it many blocks, many small blocks. It's just like this. If you see this one, so now I had a boundary value problem just over this region, just 4 points, and I make it different blocks again. So you can tell I can use many mathematical way, like some, for example, bilinear interpolation, or what I can use these things easily. But only bilinear interpolation may not work, so use some other means the dynamics also in over this region, like the physical processes, but our in land, as I told you, there are many mountains, because it's not flat. Somewhere it is mountains, somewhere it is ocean, somewhere it is forest. So many things will come in account. So I will not going into details, but just I am telling the mathematical part, how it works actually. So now I have 7 equations, 7 unknowns, and I have a boundary value problem. So now I'm coming to the back. So now what we'll do, there are actual nonlinear equations. We first make it to linear equations. We do mostly the finite difference method we use to convert the nonlinear equations to linear equations. And this method, everyone, I think the mathematical people, everyone knows these things, because if I take a by the Taylor theorem, if I have a time step, and at any point I can make it like this. If it is, this expansion, Taylor expansion, and if I just consider the first derivative of the function, and I'll find like this. And if I ignore, and if I take the higher terms very sufficiently small, I'll find like this. So all these things. So the first derivative we can convert into this, become a linear equation. And for second derivative function, for the second derivative, I can make it in this way. So now if I put this first derivative and second derivative in my original equations, wherever it is first derivative or second derivative somewhere, if I put, so all it will become linear equations. So now if it become linear equations, finally the model will find the 7 unknowns and 7 linear equations, but in the numerical way. So after that, the model will do some calculations, and we mostly use the Runge-Kutta third order time steps we mostly use, so that it will compute by the supercomputers, and we found some results. It will give us the results, and after that we check whether the model, whatever gave the result, that is how much correct this one. So I worked on this issue over India. So I simulated 30 years Indian climate, Indian temperature and Indian precipitation over 30 years by using a regional climate modeling system, which is called XCM4. Yes, which I used for 30 years over India to understand how the regional climate model works over India. And this is the first time I used for 30 years and no one used before. And to understand if this regional climate model performs well over India, then we can go more uh, details and we can use this model for future researches. So I worked on this issue, and what I found if you see, this is the model what we give, this is the temperature and this is precipitation, and this is in annual and this is different season, winter, summer, monsoon and autumn. And if you see, this is model and this is observation. If you see the model is how good and how bad, you can see here the different colors. If you compare the colors, you can see in the colors are here are the color marks, how the values are there. So mostly if I see for the winter season, I can see the model works very well. And but for the monsoon, the model is very less precipitation is given compared to the observation. It means the model is not good for monsoon season. And for your understanding, I'm telling till now, no climate models are perfect. Till now, no climate models are perfect. It means no climate models are giving the actual result what you are expecting. So sometimes we need to understand. We that's why we many times we compute the uncertainty. Whatever the result I will give, I will tell how much uncertain it is. It means how much may be less or how much may be higher. But for this study, I just tried to simulate the 30 years rainfall and temperature to see how the model works. And it took about 2 months to simulate these things with the very high supercomputer, which is available in our Pune, CDAC Pune. If you know about that, I worked there to compute these things. And so, okay. So if you see the model, if you see the model is, and if you see the mod, as I told you, model is not perfect, but some places, if you see many places, the model works very well. If you see what this region, model works very well, even in monsoon. If you see the northeastern regions, this region, northeast regions, you see model works very well, northeastern India, and also for north here also. You see there are quite similar colors. So it means whatever model gives, we are expecting the same things. So it means model is good for these regions. Although it is overall India, it is not good like here. It's very low, very low rainfall is given by model. But in observation is very high rainfall occurs. So we tell in this particular these places model is not good, but for these places northern regions model is good. Similarly over this region you can see. So it is depends on the region to region. So if you see the bias means the difference between the model and observation. It gives you more green. The values are green and light orange and light green are good actually. Model are good over those regions. For example, here model is good. In winter here model is very good, and also in India in summer season. In the summer season, if you see the desert areas, model is very good. In monsoon, if you see the northeastern regions as well as eastern regions like Odisha and the central regions, model is very good. So here also in autumn season, the central part model is very good. So sometimes, so these things, my work was to highlight model where the model is working well or not working well. So, and this is the standard errors. How much error in the model? 1 to 5. You can see the more green is more less error, and more red means more large error in the model. So the next step was to correct the biases, to correct the model. But as it was my PhD work, so I had no time to correct the bias of the model. If I would work over India, then I could correct the bias in the model and then proceed further. But that I will do also in future. And also now I'm doing this thing. Later, maybe after this, after finishing my job in Japan, then I'll go back in India. Anyway, so this is what the total presentation, total things what I would like to discuss today. And yeah, I think I finished this. So if I summarize my presentation total, so I can tell what I discussed today and what we understood. So we understood what are the climate problems. As I discussed, the climate models like our extreme events, floods and droughts and tropical cyclones. And these are our mostly climate problems. And I explained what is a climate model, and we understand actually what is simple. The climate model is, as I told you, it is just set of different equations, and that solve the climate in a numerical way. And to understand this climate model, to solve this, to understand the climate model, if you understand it well, then it mostly describe various components and fundamental laws in climate models. And we learned about basic equations, what that govern the atmosphere, and we also understood what are the numerical methods. Some numerical methods that we mostly use the finite difference method to solve the non-linear partial equations used in the climate models. And I showed you finally some researches, actually what I did in past, and presently I showed you what I do, what I my presentation today. I understand that this is a new topic for for the students, and some, yeah, although the climate point is known to everyone, but the theories and the practical things in the knowledges in it is mostly new to many people. So I hope I could make understand some of them, not all, but some of them. So if you have any questions and comments, please ask me. I will be happy to answer if possible. Thank you very much, everyone, for your attention. Thank you.
Thank you, sir, for your nice presentation. Thank you, sir, for your enlightening deliberation. Your talk is excellent and very informative. Very useful session to all research scholars, and your talk will broaden the outlook of our participants, research scholars, and students, and also faculty members. Thank you, sir. Question answer session will be conducted after the second session. Please, sir, you connect with us. Now we start our second session. This is the time for the second session. For introducing our next eminent resource person, Dr. Debashish Pradhan, Assistant Professor, Defense Institute of Advanced Technology, Pune. So, I request Professor Rajendra Kumar Swai to introduce our resource person, Dr. Pradhan. Over to Rajendra sir.
Hello. Good morning, everyone. Now, our next resource person is Dr. Debashish Pradhan. Dr. Debashish Pradhan born in 1976, is presently working as Assistant Professor in Department of Applied Mathematics, Defense Institute of Advanced Technology, Pune. He has received his PhD in Mathematics from Indian Institute of Technology, Bombay, India in 2018, which is thesis titled as Non-Overlapping Domain Decomposition Method of Elliptic and Parabolic Problems. His research interests include: number one, numerical analysis, both computational and theoretical aspects of finite element methods, FAMS, boundary element methods, BMS, domain of decomposition method, and finite difference methods for partial differential equation, and second, image processing. He has published many research papers in national and international journals of repute. The quality of his papers can be measured by the fact that the number of its Google Scholar citations is 56 and H index and 1 to 10 index are 5 and 1 respectively. His academic experience spans over a period of 17 years in top institutes of the country, including IIT Bombay, Institute of Mathematics and Applications, Bhubaneswar, Department of Mathematics and Statistics, University of Hyderabad and Department of Applied Mathematics, Defense Institute of Advanced Technology, Pune. During his illustrious career, he has received many honors and awards for his excellence in the field of applied mathematics, prominent among which are the M.N. Saha Memorial Award from the Institute of Electronics and Telecommunication Engineers, IET, in 2016, and the postdoctoral fellowship from National Board of Higher Mathematics in 2009. He has presented and published several research papers in national and international conference and workshops. Some of his Nobel publications are Detection and Resolution of Multi-Directional Motion, Signal, Image and Video Processing, Springer Volume 1, Volume 13, Number 5, pp 1001 to 1010, 2019, Robust Zero Watermarking Algorithm for Stereo Audio Signals, International Journals, Information and Computer Security, Volume 8, Number 4, pp 330 to 346, 2016, and Operator Splitting Technique with Force Scheme employed to simulate pressure, wave motion inside gun chamber, Applied Mathematical Modeling, Volume 39, Number 8, pp 2139 to 2154 in 2015. He has visited many countries, prominent among which are Switzerland Federal Institute of Technology and University of Zurich, South Korea and Canada. I am sure Dr. Pradhan's depth of knowledge and breadth of experience in the field of applied mathematics will enlighten the participant in today's webinar. Now over to Roshan.
Thank you, Rajendra sir, for your nice introduction about our resource person. Now, I request Professor Alok Chandra Mohanty to say something about the topic mathematics in image processing. Over to Alok sir. Please, Alok sir.
Thank you. Thank you, sir. Now we have arrived at the last session of the 2 days international webinar, and another emerging interested applied mathematics topic, mathematics in image processing, to be presented by Dr. Devashish Pradhan, Assistant Professor, Defense Institute of Advanced Mathematics, who was a student of mine at Udara College. In the so you have made me feel proud to be your teacher cum mentor. In this present context, this topic is more relevant to our society. So it is my great honor and privilege to have been asked to focus on this recent topic. Actually, an image is the array or matrix of square pixel, that is picture element, arranged in rows and columns. So basically there are two types of images. One is vector graphic, that is line art images. Second one is bitmaps images, that is pixel based. Some common file format for generating images are GIF, that is graphical interchange format, JPEG joint photographic enhanced group, TIFF tag image file format, PS Photoshop, PSD another Photoshop document. The purpose of early image processing was to improve the quality of the image It was aimed for human beings to improve the visual effects of people. The image processing, the input is a low quality image and output is an image with improved quality. Common image processing include image enhancement. The first successful application was the American Jet Propulsion Laboratory, AJPL. Nowadays, the purpose of image processing is to improve the pictorial information required for human interpretation, compressing of image data for storage, and transmission over network, pre-processing to enable object detection, classification, and tracking. The mathematics context, image processing is the mathematical analysis of an image. The image can be still or video, and the output need not be an image. An attempt to reproduce an image without the glare of the sun's reflection is a form of image processing. Producing a line graph of varying light intensity in separate frames from a video clip is an equally valid image processing technique. The different image processing techniques have altered how a specific image is captured, put away, or discovered from the specific sources. Generally, image processing techniques incorporate image restoration, image segmentation, image enhancement, de-blurring, denoising, and so on. Such processed images are widely used in medical images like angiography, MRI, that is magnetic resonance imaging, computer-assisted tomography, that is CT scan, and satellite images, X-ray, etc. However, mathematics has played a crucial role in different image processing techniques referred previously. It has been seen that picture preparation has a solid association with mathematics. Many of the image processing methods rely on the basic mathematical techniques of histogram, equalization, probability and statistics, discrete cosine transform, Fourier transforms, differential equation, integration, matrix and algebra. For example, MATLAB, nowadays, MATLAB is one of the most commonly used tools by the researcher in the field of image processing. There are another software is also there, Scilab, and another Maple, other are some are there. Now the application areas of image processing are television signal processing, that is NTSC to PAL, you have already seen in the TV, QVGA to VGA, video graphic array, extra video graphic array, or enhanced video graphic array, HDTV to HDTV. Nowadays we are using the HDTV, that is LED TV, satellite image processing, that is in the remote sensing, geology and land resource. Medical image processing, ultrasound, MRI, already we have mentioned, robotics, automatic inspection, unmanned operation, detect and tracking the target, visual communication, that is video call, conferencing and teleshopping, and law enforcement, that is most important, biometrics identification, that is seen in the Aadhaar card, fingerprint, face, iris. So in this topic, in my theme presentation, now I describe about the image processing. What our topic is on mathematics in image processing. The technical portion I am omitting for the eminent speaker. So our eminent speaker, Dr. Devashish Pradhan, will make all the scholarly participants comfortable about the topic within the time frame. Thanking you all. Sir, over to Prashant sir.
Thank you, Alok sir, for highlighting the topic to our participants. Now I welcome to Dr. Devashish Pradhan sir. I request Dr. Devashish Pradhan sir to share your thoughts and personal and present topic mathematics image processing to our participants. Now we hear from you, sir. Over to Devashish sir. Please, Devashish sir.
So good afternoon to everybody. Am I audible to everybody?
Yes, sir.
Yes. Okay.
Yes, sir.
Yes, sir. Visible, sir.
So it is visible?
Yes, sir. Visible, sir.
Okay. 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 I would like to thank organizing committee for giving me a chance to deliver a lecture on this webinar seminar. A special thank to Alok sir, and he was my direct teacher during my BSc, and he has taught me so many things, computer, that means computer programming and ordinary differential, so many things. So whatever I am here today, and I can thanks to sir due to because initiatives, whatever the idea or maybe background, the development happened due to sir, and also sir continuously that means interact with me for this seminar. So thanks to sir, and also thanks to everybody, and also thanks to principal sir and also HOD madam and other sirs. So now I'll start. I don't know. I'll start maybe with very basic things, and also I'll try whatever the Alok sir given the introductions, and I may cover all these things or not, but I will try my level best to cover most of the things. And also I'll tell in between the basic how this is actually happening. And also whenever anybody finding difficulty, any doubt in between, you can ask me also. That is the idea. So this is the topic I suppose to start, mathematics in image processing. Okay. First part I will discuss what is image. Whenever we are talking about the image, an image is a two-dimensional function that represent a measure of some characteristics such as the brightness or color of a viewed scene. Okay. Now, if you look at this, is actually is written in the two-dimensional function. Now, whenever we are talking about the two-dimensional function, that means how it looks like. If you see this function, this is a two-variable function. That function can be represented in this form f of xy, and where x and y are the special coordinate. What does it mean? That means like this. Suppose you can now imagine, and you are just standing somewhere, or you are taking. You can look the outside, and you are seeing the tree or anything. And if you see, this is a 3D view. But whenever you are seeing in this same thing in your computer or any movie, anything you are seeing, that you are seeing the view on the 2D. So that means what is the minimum requirement? That means we are doing a one projections. That means whatever the 3D scene is, original scene is there, that we are projecting to 2D projection plane. Okay, and that's why if you look at here the right side that image, this is the like this. If you look at the original image, whatever the 3D view, and whenever you are just taking a projections, and that will looks like this person will happen. Now whenever you will see this one, that means I can say here, if you look at this person, I can represent in the Cartesian coordinate x and y, x axis and y axis, and what will happen, and each position the value that I can able to tell the functional value, and that will give you the intensity. So what is that one? That is written amplitude of f. That means particular x and y, you will find a some value. That means you can think this way. I can write z equal to f of xy, and z is nothing but equal to each position x and y, you will find a value z. Okay. Any problem? Yes. Yes. Hello. Hello. Any problem?
No. Carry on.
Okay, sir. Okay. Now if you look at this one, that means whatever the two-dimensional function I told, The same thing, if you'll see the how this is like this is the image we have taken from this that slide. And if you look at this is the two-dimensional array x and y. And now if you can imagine like this general, suppose y equal to f of x. Now if I want to draw a graph, then y value that at position x I will get. But here what happened function, that means this is the three-dimensional things, z equal to f of xy. Okay. Now each position xy I am getting some particular value, that value you can z. And here the z is represented by ixy. Okay, because why the ixy?
Sir, 1 minute.
Huh? Is it? 1 second. It is visible now?
Yes, sir. Visible, sir.
Okay. Sorry.
Yes, sir. Yes, sir.
Okay. Okay.
Yes, sir, visible.
Okay. So now this image you see here. Now suppose that whatever the represents f of xy I was telling, that means at each positions you will find some z value. So that's why if I draw, that will give you a three-dimensional, that means function, that means z equal to f of xy, and this is, you can say, the z axis, that means particular each and xy position you are getting some value. We'll see the later stage how it is, but this one I have given in that whatever the left side you are seeing the general idea of the 3D function whenever you are plotting, and we are able to see this type of view. Now question is coming. Now whenever you are general any original natural scene we are seeing, that is the one continuous picture. But whenever we are just seeing in the computer or maybe laptop, mobile, everywhere, and that is, and all the machines are finite precision machine. Now what will happen, the continuous scene or I cannot represent in that my computer, that I need to make as a finite precision framework. So for that process we require what digitalize we need to do. But before that one, what are the requirements, how to do that digitalize? Because here you see the original scene is the continuous scene is available. Now whenever the image acquisition is happening, there are two things are there. One is maximum thing is illumination, that means light source is there. Whenever the any object is illuminated by that means illuminated a scene and absorbing the energy reflected by the object in that scene, that means whenever the reflection is happening, and that reflection is happening through passing through the imaging system, and this imaging system there are completely hardware part and sensors, so many things are vertical, horizontal, everything are equipped here in that imaging system. That means you can say that camera whatever you are just using or mobile, this is you can think as a imaging system. Now here the left side image whatever you are seeing, this is your continuous image. Now whenever through this imaging system I am seeing, here you can see the digitalize happen. That means what happened, here the scene is continuous. Now after passing through the imaging system, now you can able to see, this is the one you can able to visualize. This is the chessboard kind of thing, so many blocks are there, and here we can say this is the grids. Grid means what happened, this is, if you imagine, this is x-axis and this is y-axis, and that means each block we can tell as a pixel. Now the same thing representation whatever you are seeing here, and this is that pixels, you can say this is x-axis, this is y-axis, and that object whatever you are seeing the left side the continuous image. Now after digitalize I am seeing this way. Now what will happen, if you will take more number of grids or more number of pixels, this image whatever you are visualize here, that will give you a continuous image. That was the idea. Now what is happening here, the same thing whatever I told you, the similar way the image formation is happening. That means point source of illumination reflected on that surface, based on camera is there, then based on you are finding that image value. Okay, now suppose I want to write the same thing whatever we discussed, the illumination and reflections, based on suppose I want to write a mathematical model for that one. So now here what will happen, two-dimensional function, already in the first slide I told you this image whenever you are discussing, this is the view you are finding in the two-dimensional view. That's why that function is written f of xy, and the value of amplitude f equal to the spatial coordinate, that we used to tell intensity value. Okay. Now, what will happen? This fxy value, how this value is generated. Now, here you look at here, f of xy is a function, and which is depends on x and y, and that I can able to say as a consequence, I can say f of xy must be a non-zero and finite. Because why the finite is required? Because our machine always we are using the finite precision machine. That means, for example, I'm talking 1/3. That rational number we will consider. Now, whenever we will implement in the machine will give you 0.33333 like this. Infinite recurrence will get. But when will stop? Somebody, I'll ask this question to someone, then you will tell after decimal maybe 0.33333 up to 10 digital I'll consider. And some of you will tell maybe after decimal point 16 digit. Some of you will tell maybe 100. So basic idea, whenever you are increasing, that means you are just taking a very accurate value, or you can say the precision you are increasing. But what happened? Whatever you want, that whenever the finite precision machine you are just doing or using, that cannot give the same thing. So that time some limitation is there. So here also same thing, f of xy, whatever we have seen, and this f of xy is the some finite value has to be taken. If I take 0, that means whatever nothing I'll get. Infinity, obviously I cannot able to incorporate my finite precision machine. So that's why that value has to be in between 0 to infinity. Now, whenever 0 to infinity, now how this value is generated? This value, whenever you are generated, that two component already you have seen the previous figure, the amount of source of illumination. Another second one is the illumination reflected by the object of the scene. That means fxy can be generated by these two things. This is the two major property. One is illumination, another is reflection. So that I have written fxy in the term of ixy and rxy. Now you can look at here, f of xy equal to ixy and rxy. This is the production of the two quantities coming, illumination and reflection. Now what happened? ixy, whenever you are finding, because illumination, obviously this is the finite 0 to infinity, that is because you cannot limit. That means that's why we have taken 0 to infinity, that value lies between 0 to, because whenever the source of illumination is coming, like this general sunshine, it will see. You cannot measure. So that's why we are taking 0 to infinity, because whatever the highest precision we can able to consider our machine, that we'll consider. That is the second equation. And whenever the reflection is coming, r equal to, we are taking 0 and 1. Suppose what will happen? Suppose I will consider r equal to 0. That means what does it mean? R equal to 0 if we will consider, that will happen total absorption. That means if anything, any illumination is coming, and in that the reflection is not happening, completely absorption is happening, that time obviously will get 0. Okay, so that means everything passes through that, you can say completely absorbed on that scene, or maybe whatever the object. Same time, if rxy will become 1, that means completely reflection will happen. Okay, so obviously 100% reflection never happened, any object, obviously. So that's why we never get exactly 0 or never get 1. So that's why this value is the reflection quantity, always lies between 0 to 1. Okay, so that's why this f of xy, if I multiply this way, how f of xy has value has come, the previous slide you have seen, due to this I is illumination in between 0 to infinity and r equal to 0 to 1, and if we multiply, obviously the fxy equal to the similar will happen. Now this is the main objective. Whenever you are finding that f of xy value, these are the things always you will get. Now what will happen? Now you see here another thing here, X-ray, general concept like this. Whenever we are taking the image, so that's why if you look at any time, whenever you are going to any maybe Photoshop, then what usually they used to do, they will illuminate very big light. Idea is because if reflection will happen nicely, you can able to get the very nice image. So that is night time whenever is there. So that's why your camera, whenever you are switch on, and you have to switch on also light. That was the idea behind this one. That means image value whenever is generated, this is the main component is illumination. Illumination is not there, obviously you will not find anything. That was the idea. Same time, suppose X-ray we are doing. Now same expression whatever you have seen the earlier, same can be applied for the X-ray. But what will happen? Instead of reflection, that you have to do the transmission. That means in the that means without reflection, if you do the transmission, then that means illumination through a medium such as the chest X-rays or any X-ray you are doing, bone X-ray, everything happening due to that one. So that's why that means same thing will work for X-ray also, and same model whatever you have seen, that same thing will work. Now what will happen? Suppose I want to see, generally whenever you are seeing the image, suppose in that anywhere you are seeing like this, you can think here the left side, this is the one image is considered. Okay, now computer, whenever I'll see the what are the this image, suppose left side is the image and right side I want to see what it is, and if you computer you will see the view of this one, you will find these are the value. And because here why the 0 1, because I have represented one is the white, that means you can think image is like this, image is not like this, image is here total here to here, and wherever the seeing here white I have represented in 1, and wherever the black I put the 0. And if you take the combine this is, if you look at the right hand side, this is 4 by 5 matrix, and if I view, and you will get this is the image. Okay, you'll see the next slide also how this is actually happening. Okay, so that means basically what happened, whenever generally the image you are seeing, nothing image is generated only form of that matrix. That means f of xy we have written the initial stage, that is giving as a one continuous framework, but whenever we are doing in the finite precisions, and that will come as a two-dimensional array, which is Alok sir mentioned. Now the array whenever it's coming, that means you can think everybody plays with the matrix, and same thing. Suppose here what happened, two level we have given 0 1 black and white image we are getting. Suppose I want to draw like this, you can able to see here. If you see here like this, I want to draw an image like this, border is black, in between some different color, and B I have written white. So now suppose I want to represent same thing, I have taken a matrix, you see border I have taken 0, and in between value like this 0.5 and 1 I have taken that whatever the white one, and that means this one if I want to view, that means this value I want to draw a function f of xy, these are the value, obviously I will draw a, like this I am plotting a surface plot. Okay, and this is the 3D view you are seeing, but general concept, whenever this is the original 3D view, now whenever you are projecting on the 2D plane and you are seeing this is the image, and which is as usual we used to see in the general. Okay, now question is coming, then how this is happening the digitalize, because digitalize whenever you are doing, now idea is coming, number of pixel is come to picture, or you can say that somebody used to tell picture elements. Now what is the picture element and what is the pixels, you'll see. That means here one interesting thing you see here, suppose if you look at this is not the as usual Cartesian coordinate. If you look at here, generally Cartesian coordinate whenever you are taking, this is what, this is x-axis and this is y-axis, but here completely I have taken the different, because this is y-axis and this is x-axis. Now what is the idea, why we have taken this way? General idea, if you will see the matrix, any matrix you start, matrix whenever I have started, always will start with first row, then we will move to second row, third row, like this. Now you can think that previously all these things you are seeing, suppose you can view here, and this is a matrix like this, this is first entry, second entry, that will first row, first column, first row, second column, first to third column, like this. I'll move to second row, third row, like this. Okay, so that means this row is represented for x-axis and column is represented for y-axis. In that framework, this is the image axis is designed. Image axis due to the matrix, from the idea is taken from the matrix based on this, y is the column, x is the row. That was the idea behind this one, and each point f of xy value you will get accordingly. Now what happened? Now next questions. Now here another things I'm just introducing here, then how to digitalize. Idea is two concepts will come to picture. One is sampling, another is quantization. What is the idea? What is the idea behind this one, sampling and quantization? Sampling whenever you are doing, that means you are discretizing the space. That means you can think here, suppose this is how many, this is 7 columns are there. Similarly 8 or 9 rows are there. Suppose I'll make this one is 20 or 30, 20 by 30, then what will happen? More finer will get, grid you will get. So in that process what will happen? This image, suppose I'll represent here, you may get some kind of the block kind of zigzag things you will get. If I'll take the more finer, and obviously whatever they are looking for, this image, suppose I will represent, you will get looks like same image. That was the idea behind this one. This is the digitalize in the XY. So XY, whenever that means the space, whenever I'm discretizing, that I'm doing the sampling, and quantization whenever I'm doing, that means I'm intensity value. Intensity, like this previous slide, all time I was using this value 0.1, 0.51. Similarly, what are those value we can take? Quantization will come as a intensity value. That means Z equal to f of xy. What are the Z value we can able to consider? That was the idea behind this one, quantization. Okay, we'll see. So there is the same idea. So like this quantization, as I told, this is the 0. Suppose this is, you are considering the white. Okay, this is the opposite way I supposed to write. This is 0 is the black and white for that 255. Basic ideas. Now question you can ask here, so why we have considered 0 to 255? Because you see here, this is 0 for black and white for 255. Basic idea, generally the machine, whenever we are using 8-bit machine we are using, because you know computer, whenever this is the decimal number, if you take 255 if I will take, then what will happen? 255 I can able to represent all the 8-bit 111 each. So that's why 8-bit machine, whenever I'm using the decimal number, if you consider as a 255, that will 8-bit, all the bits will give you 111 each bit. And 0, whenever I'm considering, each bit I'll consider as a 000, all the 8-bit I'll consider. So under that idea, 0 to 255 is coming to picture. That means what happened? Earlier you have seen 0 and 1. If I'll take the my level, I'll use 0 to 255. That means different level of intensity I can able to use. So in that process, what will happen? That means different color combination I can able to generate. That was the idea. Image intensity digitalization or quantization we are doing. Okay. Now you can able to see here the spatial resolution, whatever just now we have seen. Now you can see this is 256 by 256 pixels, and you see the image. Now whenever the same image size is, I'm keeping as it is, but 128 by 128 pixels. That means what happened here? Pixel size, suppose I'm just considering half inch, but half inch. Here what will happen? 1 inch by 1 inch, because image size is same, but only pixel size is increasing. Here also what happened? This is whatever the pixel size. Here pixel size is increased by 4 times. Now you can able to see image size is this one, and this image. If you will compare, now you can see the zigzag kind of things are there, and you can see here, because all the 4 image size of the image is same, but here number of pixels use the very less number of pixels. Due to this one, you can able to compare. So that's means what you learn here. If you take more number of pixels, obviously you will get that more number of, that means very quality image you will get. So that's why generally whenever you are purchasing the camera, always your first question you used to ask, what is the megapixel of this camera? That was the idea behind this one. If you take the pixel, each megapixel means very high megapixel camera is there. So obviously if you will zoom that image, whatever the image you are acquiring or capturing, and if you will zoom sometime, and that will not bracket kind of things will come to picture. That was the idea behind this one. You can able to see, if because this image if I'll zoom, obviously like this issue will come to picture. That was the idea behind this one, the spatial resolution. That's why generally whenever you are purchasing, the idea behind the why you used to go for the megapixel. Okay. Similarly, now here also the similar way, same image size. Now you can see I'm just making what number of pixel use the here same, number of pixel use same, number of pixel use same, number of pixel use same. Here all the cases I'm use the number of pixel is same, but here what happened, number of pixel if I'm using same, that means pixel size is decreasing. Here 1 by 2, 1 by 2, 1 by 2, but you can see here to here, because if you see this last one, if I enlarge also, that you can able to generate this image, the left side image. But whereas that image size you see, suppose I'm just here to here half, then after that half like this pixel size. Now you can see the last image is degraded. So that's why always you maintain the number of pixel has to be used, more number of pixel to generate picture. Then what will happen if you zoom, that decreasing will not come, or you can say degradation will not come to picture. That was the idea. Okay. Now image quantization, how to use that, how many number of that means intensity level like this earlier slide you have seen already, 0 to 255. Here also the same thing. How that is coming, as already I told you, NC equal to number of bits 2 power B equal to number of bits we are considering, that means 2 power 8, that NC was coming 256. Okay, so 0, because 0 we are including 0 to 255, so that's why the 256 level we are getting. So that was the idea behind this one. Okay, 2 power 8 bit. Generally if you take the 16 also bit you can consider, but what will happen, large amount of space and also transmission, so many issues will come to picture. So that's why, because if simple image, whenever you are considering, if you will not use more than 8 bit, if you will use, then special attention has to be taken care for this transmission. Whenever, because only you cannot generate that image, because that image has to transform to somewhere like this. Whenever we are getting the video, if that image size is very large, the downloading time also more, all these things, and also internet capacity, so many things issue will come. So that's why in general always people used to use 2 power 8, that means level is 0 to 255, and this is 2 power 8 is 256, and level we are using that. That was the idea. So this is the way the intensity level. Now you can see f of xy 0 and 1, that I can say 0 is black, 1 for white. Similarly 8 level whenever I am using, what happened, 0 to 255 I am using. Now if I use 16 bit, that means what happens, 65,536 is coming to picture. So that means this much level, obviously you will get very nice image color combination. But what happened, very horrible situation will come whenever you are transforming from one place to another place. So that's why generally 8 bit everybody is happy with this one, 8 bit generation is happened. So that means that sampling you can able to see, this is original image. Now whenever the 8 factor, that means this is 256 is used, this is 128 level is used, you can see the how much degradation is happening. Now this is used only 64 number of intensity level. Now you can see this is only 32 levels is used. Now you can see this is 256 level used, this is only 32 levels intensity value used, generated the same image, and obviously the degradation you can see. Similarly, as I told, if you use 65,536 level, so obviously very nice image you will generate, because very nice image. But that time also that image, that means space will come to picture. Now next question, as I already you have seen the matrix, this is my image axis, y axis, this is x axis, and you can say which why this is image matrix form is coming, because that is the representation is coming to the view, and all the value if you will see in the matrix form will come to picture, xy. And also in general, whenever the coordinate system, always you used to write 0, 2 and -1, that means this is one image, like this general image if you will click anywhere. Also your smart TV, whenever you will open, always you will see 1263 by 1793 into 3i something. What is the idea? That means number of row, number of column, and how many that means different position you are just using. That was the idea. That means first two position is number of row and column. So that's why number of row is m number of row, this is number of column. But general software whenever you are using, this is start from the software 1 to n, like this. If you use the MATLAB, always the indices start from 1 to n. So this is the general notion. So that is not a. So now same thing what earlier we discussed, image is a function, okay, and that function f of xy, and I varies from 1 to n from this way, and j varies from 1 to m, okay, and image a matrix ij whenever I'm that means I'm a representation giving in the matrix form aij, and in gray level range of the value, that means aij all the entry you will get already. Previous slide you have seen 2 power k, that means level I'm using l, suppose this is k is the bit, 8 bit I'm using, that means what happened, l equal to 256 and 0 to 255 level aij all the entry like this, whatever the dotted line you are seeing, these are the positions you will get always 0 to 255. That was the idea. Now what happened after that, similarly other things. Now how many numbers like this general, whenever how this is calculation is happened, any image, what is the size of this image. Now what happened, now here I'm using m by n number of pixels, and this is the my bit is I'm using 2 power k level. So that means how to calculate, you see here. Any image size you are suppose you want to calculate number of row, number of column, and k bit. So that means each bit I require 8 bit. So that means n number of row, number of column into 8 bit I'll multiply. That is the image size is generated. That was the idea. So like this, whenever you are telling what is the size of image, so from this last equation you can able to calculate what is the image size. Okay, and number of bits. Similarly, color image if I will do, so what will happen? 3 different component will come. One is RGB, that means red, green, and blue. Later slide you will see. So in this case, what will happen? Whatever you are getting, another k, 3k will multiplication will come, happen, because one red component will come, green component, and blue component. Okay, this is we'll see. That's why 3k will come to picture. 3 into this same thing will come to picture. Okay, now same thing what I told the Aij, that is the matrix. All the time you will get the image in the matrix form. Okay, that's all already we have discussed. Now you see here, this is the original image you got. Now suppose I want to somebody, you have seen the Photoshop, or also your computer, if the Photoshop is there, and simply you are rotating, you are using some command to rotate. Now what happened? What is the basic idea behind this one? The software development whenever is happened, this is the original image A. Now you are seeing the transpose of A. Simply you see B equal to A transpose I have taken. Simple this image I am getting the transpose, that is a complete, there is a transpose image I am getting. Now suppose I want to flip that image. Now you see here, flip the image, this is the original image. Now I am getting the B. You see here, only simple that equation, the flip Aij is there, only reverse way, whatever I, that value equal to j minus that particular value, that you see this image to this image. Like this you are seeing the all the Photoshop and how it is happening. And also if you know some little bit programming, and you can try, this is the only simple for loop you use, and based on you can able to any image is there, and you can able to generate these type of things. Okay, similarly crop also, sometimes suppose you want to particular things you want to view, and simple crop you want to do, and simply you see this matrix particular position I want to take, based on I can able to get a crop. This is this like this what I want to say, whatever the image you are seeing, basic idea generated based on the matrix. You have to play always with matrix. If you know the very good, that means all the everything in the matrix, all the whatever you can say that. But here one thing you remember, whenever you are multiplying or anything you are doing in this case, always happening the point-wise multiplication or division. Image case, all time you are the, whenever the multiplication you are doing, you need to ensure that you are doing all the calculation in the point-wise. Now similarly, now you can see the binary image. One example I am telling the matrix, as I told, suppose this particular portion I am seeing, you can able to see 0 0 0 0 0 1 1. This is the view. Similarly, this is the grayscale image. Now suppose I want to view this one particular intensity value, as I earlier I told you f of xy how the image intensity value generated, and these are the intensity value grayscale, and the particular positions, this value you are getting, and this is image you are seeing, but that is nothing but equal to matrix with all the entries. That's all. Similarly, suppose this is the color image I am considering, as I told, red, green, and blue. Some color image you are seeing this one, and these particular things I will view. These are 3 individual component you will see. One is red component, first one, green component, blue component. But here looks like this is the completely red, but this is not only the one single component, the combination of all 3 based on you are seeing the color combination. So that's why whenever you are playing with the colors case, always that is capacity, that means whatever the storage capacity is required more. Okay, I'll move to quickly. Now similarly, now simple, you see here I have generated like this, this is original image given, I have generated the matrix. Now I'll show you here, this is the image I want to generate. Now one matrix I have written, this matrix, and I have generated an image. You can see first one is the completely black, this is 1, this is 2, like this is 255, I am considering as a white. Now I have generated 256 by 256 image size. Now similarly, suppose I want to generate a circle. Now you see this is white, this is black, so that's why I have taken a one circle formula in the like this, you know already, Bij equal to matrix 255 in this radius 80, the radius I have taken 80 pixels, radius means 80 pixels, and this is my center positions 0, otherwise based on I am getting this value. Similarly, suppose I want to, now you see this one and I want to construct an image like this. Previous already image you have seen this one, and already you have seen this image. I want to generate this one. 2 image I multiplied. Now you see 2 image, the previous image I multiplied. But here what happened? I have divided by 255, because ideally what happened? Because as you know, always I am considering the intensity level between 0 to 255. So that's why 2 image suppose 255 multiplied. Obviously that will happen more than 255. So that's why we are making a normalized, that purpose 255. So that's why whenever you are playing with this, always you have to take care, normalize you have to do. That was, you see. Now next image, what happened? This is the image. You can see here. This is the one MRI scan. Okay, you see here the left side the MRI scan. In that scan, and this is your spinal cord, and whatever the crack, anything is there. Suppose I want to enhance like this. Whenever they are taking the image, you are getting the left side image. Now suppose you want to make an enhancement. Now you will see the how the simple mathematics is involved here to get this one. You will see now here, because generally whenever that machine is taking this X-ray in the spinal cord, and you will get this one, then after processing, because you are getting this one, now that processing whenever you are doing, these are the simple mathematics is involved here. So how that is happening, that part I will tell quickly. Same thing here, you can see this is one bone X-ray. Whenever the bone X-ray we are doing, and we will get usual images like this after doing the process, but this is not one like this one only simple one transformation technique. But whenever I'm moving from here to here, this will not give you only one step. I'll reach with this one. Here there are lots of transformation involvement is there, but very simple transformation techniques are there. Based on I will get this one. Similarly, here if you'll see one circuit board is there with lots of noise. If you see the dotted line, that is so many salt and pepper noise are here corrupted with that circuit board. This way I want to remove this noise and I want to get this one. Then how to remove this noise with that technique, that you can say that median, that statistical technique, mean, median, mode, all these things. This is a very simple concept, median, using how we will remove that we'll see. Now here what happened, as I told, is the basic transformation we are doing. Now image already you have seen, this is the one matrix. Now f of xy, any positions there, I am simply transformation linear algebra, already everybody has known this one, the transformation. That means one transformation I am applying on f of xy, I am getting the new gxy. Already everybody knows, that's why I am not talking about this one. Now what is t, that we need to identify. Okay, so this is the same thing. This is the original image. After applying transformations, we'll get the enhancement like this. This is the transformation that correctly, that what is the transformation that we need to identify. Okay, so like this, here you see one transformation in the contrast stretching. What is the idea here? Like this, suppose this is my 0 to r. 0 to r, what is the meaning of the 0 to r? This is 0 and this is r is, suppose this is I'm taking 255, that is my white range, and I want to change s equal to tr. And okay, if you look at this one, gxy equal to I have taken is s, f of xy, because that convenient notations I have taken f, instead of writing f of xy I have taken the r. Gxy equal to I have taken is s. Okay, so that's why s equal to tr. Okay, so that means whenever I will apply on this transformation, I'll get the new value, and that new value is updated in that s axis. That was the idea. This is r axis and this is s axis. And also already you know r is the only one dimensional, because intensity value whenever I'm finding, always you are getting only one value, because 0 to 255. Now because what happened here, contrast stretching whenever we are discussing, that means here to here we are not changing any intensity value, as it is we are keeping. Here to here also not changing, but in between here to here, and we are stretching to directly towards the white. That was like this one contrast stretching idea. Similarly, thresholding, what happened, whatever the value before k will make it 0, and after k will make it white. That means what happens, suppose I want to generate a one black and white, and based on I can use this thresholding. Now these are the like this transformation, linear like this. Okay, I'll not tell, because one transformation is used. You can see that transformation I was telling, one transformation you can think the logarithm. Instead of that transformation t, I have used the log function, but instead of log r, I have taken 1 plus r. Idea is why the 1 is considered here. because if you look at, we are considering the intensity value lies between 0 to 255. If I'll take r equal to 0, so log value is not defined. So that's why 1 plus r we have taken, and which will not changes major things. So that was the idea, but this will well defined. So s equal to, instead of the transformation, I have logarithm function I have taken. Okay. Similarly, another transformation of power law transformations, r power gamma. Okay, c into r power gamma. That means transformation is there. I can say the power law transformation I have used. Okay, and that means r equal to whatever the original intensity I have taken, that power is gamma. Okay, but in this process, what will happen? The narrow range, that means small range of this value is there, I can make is white, and whatever the whiter range is there, I'll not change anything. That was the idea behind this one. And in the calculations, I'll take the c equal to 1. Now you see the next example. This is the example we started, that whenever the generally that that MRI scan we are doing, that you used to get this image. Now after processing, now you see gamma equal to, this is the transformation, r equal to power gamma, gamma equal to 0.06 I have taken. You see, at least this much white I got. Similarly 0.04, now you can able to see. That means what happened here, black, this portion, because this is white is there, I am not changing anything, only this portion is white, is towards black is there. I want to make this portion is white. Okay, so that's why you can see here gamma equal to this one. Now this is became is white. Now this is gamma equal to solar 0.4. Now you can see, earlier you can compare with the previous one and this one. Now gamma equal to 0.3. Now you can see here, and you can see this is original image, different value of, and you can see here. Now this is clearly visible, the last one, and this is the very simple transformation technique based on, and we are the spinal cord, the fracture of the human spine cord, you can able to identify, a doctor can identify. That was the idea behind this one. Similarly, this is, you can say, the one runway, and if you look at very nicely, and this is completely not that much clarity is there, because totally white kind of things are there. That means white pixels are more. Now I want to, if I want to see more visible or more pleasure way, then I can tell, if I'll make in the towards black, and that will give you very nicely, or this is very pleasant image, you can say. So same way, now you see the previous one, because what happened, dark to white I was doing, I was taking gamma value equal to very small, in between 0 to 1. And if you take gamma equal to more than 1, now you can see, if white pixels are there, that towards that image is coming, you can able to see this is coming towards dark. And similarly, you can see here, this was the original image is there. Now r power, you can see. And also one thing you remember, image processing or image, and these are the things, whatever I'm talking about, this one, this is processing. That means original image is this one. After processing, you are getting this one image. Already initial slide I told you, these are all this in processing. Now what is the processing required? And also, because this is completely subjective, because everybody may or may not like whatever the image is there. That's why maybe some of you told, maybe tell that this image is very good, some may be like this one, some may like. So that's why this is completely subjective. It is person to person varies. Okay, I cannot say this is very good or this is very good. Okay, that is up to you. Similarly, you can see here, this is like this contrast stretching kind of things are there. What happened? You can see here dark is there, also white is there, but I want to make, now you can see here, here and here. Here what happened? I have not changed anything in the dark side. I have not changed anything in the white side. Only I have make the stretch in between. That means in between, like this. This is not the one way. You have to hit and trial way. You have to do. Suppose whatever the position you have to take, it will stretch, and what are the things you are gaining, you can able to see. Like this, here to here stretches. This is my original image, and this like this. You can say this is nothing but equal to one piecewise transformation we are using. Everybody knows that what is the piecewise. Like this, you can think piecewise instead of the transfer. You can think the piecewise function. Three different level we have written. Here to here one function. Here to here one function. This is another function, and this function. That's why you are seeing this. Now next one is the histogram. But here what happened? All these things after seeing, I was deciding which technique I will use. But all time also that cannot be tell. Seeing this image, you cannot able to judge which method you have to apply. So best way to understanding the problem, if you use all time the histogram of the image, and you can able to judge or you can able to think what are the next step you have to follow, or you have to identify, or you have to use, that you can decide based on the histogram. Now what is the histogram? Everybody knows. Okay, so like this is the, suppose image is there. Now I will take the histogram. This is the black, 36 pixels are there, white also 36, this color another is 22, white is 130. So like this. Now you see here, this image whatever is given to you, if I take a histogram and these are the value you will get. You can ask these questions because I'm talking about 0 to 255, but here 0 to 0.9 is there. Idea behind this one, we have normalized. Sir, can I take another 15 minutes?
Sir,
Yes,
sir. Sir, yes.
Okay, sir. Okay, sir. Otherwise, you tell whenever. Okay, sir. So now this is 0 to 9.9. Why we have taken? Because our intensity level is 0 to 255. This is whenever the representation we have done, this is only normalized. That means what happened? 0 to 255, it will normalize and we can make it a 0 to 1. So this is the normalized form is written. Now what happened? If you look at this image, why the all time you will see, and this is the famous image because whatever the requirement, the processing, all the that means features, everything is available in this image. So that's why all time this image is everybody always they will to refer. And if you see this image, when you will tell this image is good or bad. Now if you look at this histogram, if histogram is spread throughout that total intensity axis, that means this is my intensity axis 0 to 0.9, which if you write 0 to 255. Now if its intensity is spread throughout this axis, then you will tell that image is obviously good image. Okay, now you see here this image, if I take a histogram, now you see that darker part is there, only left side is there. Okay, same thing if this image you will consider, now it is the right side, the histogram is there. Now this image you will see only in between. Okay, that's why if you look at this type of image, earlier I was stretching only inside that part, I was stretching, and left side right side I was not doing anything. Because why I was not doing? Because I don't have any intensity, left side portion is there, right side portion, only my portion was only in between portion. That's why I was doing the stretching only in between here, like this you can say the 0.35 to 0.55 that I was doing. Okay, similarly you can see this one, the last one. If you look at here, this is looks very good. Now you see the histogram spreading everywhere. So that's why whenever any image you are finding, and suppose you want to see whether this is good or bad, all these things, if you take a histogram, and that will give you the idea. Now question is how to make that one, the spreading. Now here what happened, these are the example already you have seen. Now one idea is, suppose this is image is there, or this image there, I want to make the last one. Now suppose how to do, this is the one idea. This is histogram equalizations, because basic idea what happened, one transformation technique you have to develop. In the transformation technique what happened, this is like this. If you see the transformation is happening 0 to 1 to 0 to 1, or you can write 0 to 255 and 0 to 255. This is normalized form is written, or somebody can tell 0 to L minus 1, 0 to L minus 1, because this is fixed point form is, because whenever the domain and range both are same, you know this is the fixed point form is happening. And here this t, whatever the t are defined, this function has to be single valued function. That means, okay, single valued, you can say sin x, sin inverse x. Okay, sin inverse x is not a function, but sin x is a function, because sin x is that all single valued function you will get. Similarly this t, whatever you have to define, this has to be single value, and that has to be monotonically increasing. With the help of this, and we can use some, this is probability distribution function, PDF function, this one. With the help of this, is if I'll consider this tr equal to integration 0 to r and pru, and obviously always that whatever the two property, all time this will satisfy, and using the this pr is nothing but equal to probability density function, and based on we can generate a transformation technique, and based on we can able to get. Now this is the idea happened. All these things whatever you have seen, this is happening the point wise. That means point wise means, what does it mean? That means each point I'm doing the processing. But here what happened, other processing is the neighborhood technique. Neighborhood technique means what happened, suppose I want to process in these positions, but I will consider in the neighborhood of this one, and I have to do the process. That was the another technique. Okay, this is also very famous one, because all time also pointwise will not work. So that time we need to move the neighborhood technique. So now the neighborhood technique, whenever I am telling, so these are the statistical minimum, maximum, median, all these things you know. These are the neighborhood, like this maximum or minimum. Like what does it mean? If I take this value I want to update, I'll consider all the three. Suppose minimum operator I'm using, among this 9 value, which is the minimum, I'll update this one. If I'll consider as a maximum, all this value and 9 value I'll consider, and I'll update here the maximum value. Median, similarly, I'll consider all the 9 value, whatever the median value I'll consider, and I can able to update here. That was the idea behind this one, the mixed median. Now, similarly, another is arithmetic operation or logical operations. Here what happens, suppose I want to get this particular portion, then what happens, another AND operator I'll use with mask this one. If I'll use the AND result, obviously what happen, physical AND if I'll do, so this will come only this much, because this is white, and this will get, other things will get black. Similarly, or if I'll use, this is the mask you have to consider. So like this you can see, this portion I'm seeing OR operator. Now here this is a very interesting thing. Subtraction, image subtraction, what happened? F of xy there, h xy. What is the idea? Why this image subtraction is required? Suppose somebody, in person is not, maybe not like this, whenever he is going to hospital or anywhere, so after injection, maybe that body is 100% suppose working or not. Doctor want to check. You can think, before injection you can take a image. After injection you take a image, you subtract. Okay, and you will see whatever the inject, that whatever the, whether this is the everywhere, this is the moving is happening, or maybe any functioning or anything, you can able to check. Because but whenever the image subtraction you are doing, but both same image you have to consider. That means before and after same image. So after doing that, that means you can see here an image taken after injection of the contrast medium into the bloodstream, and which subtracted, and you can able to see where the injection is working or where the movement is happening. That was the idea. Best one, because anyway, if we'll go through the details, you can able to understand, because simple that subtraction is applied. Okay, same time the statistical technique. Here the statistical technique, what happened, one global mean and this is global standard deviation is used, and using this one, and we can able to do also the processing. That means the transformation technique, whatever I was telling earlier. Similarly, gxy equal to e is a one constant, f of xy, and this f of xy, whenever I'm just writing m of xy, that means this is the small neighborhood. This is mg is the capital global mean. This is the small, whatever the small neighborhood you are considering. Best I can able to small local mean I can calculate, and here also the local standard deviation I'll calculate, and based on this formula I can able to enhance that image. Like this you can see here, this is the one tungsten wire, and you want to see whether this is, all these things are correct or not. Now if you see, this is the white, and if I do the processing the previous way, whatever you have seen, and that will make like this completely white to, then that will make it white. But I don't want this white portion, I will not touch anything. I want to only, suppose you can look at here, this portion I want to enhance, this particular portion I want to enhance. Like this I'll use this technique, whatever this standard deviation technique. That means whatever the small portion is there, and I'll use based on, you can see here, this is the original, and this portion is not changed here and here, and only small portion here you can able to see here and here, and but this one is what happened, image enhance the global histogram equalization. Just now you have seen, because this is a throughout everywhere is applying, but here whenever you are seeing, only wherever is required I am just doing. That means just now this technique is used, this is locally is used. That was the idea. Okay, now after that I'm not telling how this is processing is happening. This filter, whenever, okay, this filter like this, you have seen this one. This is the statistical technique we have used. Now similar way also, other way you can do. This is suppose 3 by 3 small neighborhood I consider. This is my original image. I'll do the correlation or convolution I'll apply. And this one, whenever I'm doing the correlation or convolutions, and convolution whenever you will apply, this will rotate 90 degree, sorry 180 degree, and you will multiply with here. That means z will multiply with a. Okay, sorry, R is multiply, this is 180 degree rotate, and we'll multiply here. This is simple that this is correlation happened, but convolution whenever you will do completely rotate and you will multiply. But this is correlation, that means simple point-wise multiplication we are doing. After processing, enhance image, whatever the multiplication, the result you will get enhanced in this position. This is the general concept of the spatial filtering. Suppose I'm just taking the neighborhood 1 by 9, 1 by 9, all these things. I'll multiply in the original one, and in this process, what happened? I'll make as the image is blurring. And sometimes now you can see this is the original image. Now if I'll take smoothing 1 by 9, I'm multiplying. Now this, what is the result? 98 point. Now original was 106. Now after the new value is coming. So this is the way you can able to make a smoothing. Now you will see here what happened. This is that your circuit board with corrupted with noise, and you are using the average filter. Average means this idea just now you have seen. But what happened? Noise is there also averaging. Same noise is also coming here, but whereas if I use the median filter, the statistical technique you have seen, now you can see here. So that's why you need to choose also smartly which filter you need to use. Now you can see here, very simple median I have used here, and based on I got the remove the noise from the circuit board. That was the idea behind this one. Now similarly, another is partial differential. Everybody knows the partial differential equations. I want to some particular things, suppose I want to highlight. And how to do the highlight, that I'll use the partial differential equation. What is the idea behind this partial? How to generate this one? Suppose you can see this image. This is one point is there. I'll draw a line through this point. That means what happened? This is black and one point is there. This is the one discontinuity, and also this is white, and like this. If I'll draw this one, I'll see the what is the profile of the intensity. Now whenever I draw the line, now you can see the intensity like this. This is 5, 5. Then after slowly decreasing towards black. That's why 5, 5, 4, 3, 2, 1. Total black 0. And simply this white dot is there. Simply I isolated point. I got 6. Then after that this is 0. Then 0, 0, 0. Then after that here one line is there white. That's why I'm getting 1, 3, 1. So like this I'm getting, these are the things. Now what happened? That means why the partial differential equation is applying? Because idea is, whenever you will read, because this matrix whenever is like this is one row I consider. So if you take all the row, then I can able to tell what is my image information. Now suppose I want to find where is the discontinuity, where is that edges, all these. Suppose I want to find out, or I want to highlight. Yes sir. Yes sir.
Sir.
Continue.
Yes sir, yes sir. So then in this process what will happen? Now we will find out what is the neighborhood pixel, how it is happening, and this is simple partial differential equation you use. Now you see del F by del X, and this whatever the right side you are seeing, this is the Taylor series expansion. From that one, this is the finite difference formula. Okay, and why the del X, or you can say the del X is not called H, because general formula is what happened? X plus H minus Fx by H. And why I consider H equal to 1? Because you know the pixel 1 to 2, only the changes is coming 1 unit. So that's why H equal to consider is a 1. So that's why denominator is H equal to 1. So that's why that is not written. That was the general idea. Okay. So clear to everybody? H equal to 1. That's why denominator H is not written, because each pixel, one pixel to second pixel, unit is increasing only 1. So that's why H is here 1. Okay. Now if you take a derivative, you can see here the discontinuity was here, these positions. Now if I take a derivative, first derivative, now you can see here zero crossing is happening. That means what happened? That's that formula, this formula I used based on I got the profile, the derivative, all the point. That means 5 minus this formula 5, 5, 0, 5 minus 4 minus 1. So like this formula is used based on all the value or each point I got. Obviously last point I will not get. And this profile I have drawn. This is the original profile. This is the derivative profile. Now if you study this one, you can able to identify where is the discontinuity. You can see here one zero crossing is there. Here also zero crossing is there. Now if I move to double derivative, now you can look at double derivative similar fashion I can able to write. But this one I am writing with the help of the Taylor series expansion. Okay. Now double derivative, you see here double zero crossing is happening. Here also double zero crossing. here double click. So that means whenever if we'll take any images there, if we'll use the second derivative, obviously that will tell you where is the discontinuity or where is rem or what is step, all these things information will get that derivative. That was the idea behind this one. Or you can say the edges. So that was the idea behind this one. I'm not reading this one. So now here what happened? Idea purpose, I told you the one-dimensional way. Now because our image is two-dimensional, that means f of xy. So that's the same thing I have represented in the Laplacian operator, and similar fashion I have written in the xy form based on all the coefficient. If I'll write this is one filter, I'm getting 3 by 3 filter. That means Laplacian operator 1 1 minus 4 minus 1. Okay, based on this one, now you see this image. I'm just applying the same Laplacian average filter, similar way the Laplacian filter I applied. I got this output image, this one, but this is not that much present, that image I'm getting. Now what happened? I have applied once more gxy equal to fxy minus Laplacian whatever just now you have seen. If I apply once more fxy minus with that one, now you can see this one you got, and I have subtracted. This is original image minus Laplacian one, and you can see, you can compare here this one and this one. Only simple operator I've used the Laplacian. The Laplacian where you got in the second order derivative from that formula we have generated. You can very nicely, you can visualize how much changes is this one and this one. That was the idea. Okay. Another things, anyway, this is the different versions are there. Similarly, first derivative, where is the use? I will not tell the in details. Now you can see the suppose edges I want to find. Here you see in the application point of view, this is the one you can see. This is the one contact lens is there. If somebody want to identify where is the crack or break is there, and this portion, now cursor portion, you can see at 4 to 5 o'clock the image is crack is there, this portion. I want to find where is the crack in this one. This is the edges, and this is the Sobol operator. This is what is the Sobol operator. Similar way, first order derivative using this is the operator. From this formula we are generating the Sobol operator, and based on we are able to identify. You can see here this is the contact lens. Based on operation that we are using, this you can able to find, that is that you can able to find where is that defect on that contact lens. That was the idea behind this one. Now we'll come back to this one. Here that image we started, this is here, you can see that is the bone scan is there. I want to do enhance for this one. What we have done here, you see the Laplacian, just now you have seen the Laplacian filter we have used, that I have applied on this one. Based on, then after that sharpen, subtract with this one, already this one b minus a minus b. After that I got c. Then after that what happens? Sobol operator, the last one, whatever you have seen the past using the first order derivative, I got this one in the d. Then after that what happened? Then averaging filter, that averaging, this is 5 by 5, like this you have seen 3 by 3. Instead of 3 by 3 we have used 5 by 5 filter. Then after that you got this one, because idea is here why we are doing, because we are smoothing we are doing. If suppose fine details are there and you can able to make it smoother. Then after that product of E and C. C is what? C is this one, you multiply with E, this E. Then after that you are getting this one. After that you see sharpen image with the sum of A and F, and based on you got this one. And after that finally the power law transform, what you learned the earlier slide. After applying we got this one. That means here Laplacian filter, Sobol filter, averaging, and also sharpening, power law transform, everything we use. And you can see this is the original image, and we got the final image like this. Okay, now I'll quickly, sir, another how many minutes you said quickly, then I can conclude something. Yes sir.
Or maybe.
Hello? Yes sir.
Sir, only 5 minutes.
Okay sir. Okay sir, 5 minutes I'll conclude something. Okay sir. So then here what is the another is a Fourier transform. Fourier transform means what happened? Basic idea, please try to understand. Like this, suppose we are doing anything in the Cartesian coordinate, f of xy there. Similarly, somebody will doing in the polar coordinate. Suppose the circle somebody wants to draw, draw the circle, then either you can do the Cartesian coordinate or polar coordinate. But in the equation, what will happen? X square plus y square equal to, suppose circle 4 you are taking. Similarly, polar coordinate, x equal to 2 cos theta plus y equal to 2 sin theta, and you can draw that one. But here what happened? But you will get, both are will get the same output, but provided coordinates are different. Similarly here, whatever you have seen till now, all these things I was doing in that special domain. Now same thing can be done in that Fourier domain. That means what happened? This is Fourier domain, or somebody tell is the frequency domain. But what will happen here also? The completely domain is changing. But anyway, I will not tell, because here the frequency domain, before doing the frequency domain, you need to understand what is the Fourier transform. This is the one-dimensional function is given. Similarly, that has to be also same way the discretize we have to do. And this is the equation is given, two-dimensional Fourier transform. Okay, I'm not details, I'm not telling. Now, one Gaussian low-pass filter, similar way, whatever we have done in the special domain, same thing, Gaussian low-pass filter we are applying. Based on, you can see here, this is the one text is there, simple text is there. Now, this is the one filter we are using. Okay. Now, what happened? Because here, what is the difficulty? Some like this, if you zoom, that is the breakage line kind of things, the broken characters are there. But here, whenever the filter I'm using, you can see here, so there is no broken characters are there. Similarly, very interesting thing, this one, everybody is, because generally the Photoshop, they used to do that very, because general image, whenever we are going to the Photoshop, they used to do what? That wrinkle, suppose some wrinkle is there or some spot is there, they you want to remove. Now you can see the first image, these are the so many wrinkles are there. Okay. Now second one, you can see here that whatever the low pass filter you have seen, this very simple filter is used. Based on, you can see here that wrinkles, all these things is removed, and this is d0 equal to here 100. Similarly, d0 equal to 80. Now you can see, you can compare all these three wherever the wrinkles are there. So that's why the Photoshop background completely mathematics is there. But we are, because we are not seeing that one. That's why you are thinking, okay, Photoshop maybe some special things which are there they are doing. But background is complete mathematics is there. And here the Photoshop is what? Fourier transform is used, and Gaussian low pass filter is used. Based on, you are getting that whatever the smoothing you are doing, that was the idea. You can see here, and this is here, completely smoothing it. That was the idea behind this one. Okay, this is the Fourier domain. Similarly, suppose here the one noise is the periodic noise is there, I want to remove. If I do the special domain, what will happen? This is the throughout everywhere the noise is corrupted. Now what happens if you take the frequency domain, the Fourier domain? Now you can see this periodic noise that will come in the circle. That is actually in the frequency domain. You can see the properties based on the imaginary and axis, and you will get that is symmetric with respect to origin. All the you can able to have a look. Based on, now if this dotted line you can see is the my noise, I will reject. Then after that you see this dotted line I will reject, and based on here to here I can get. These are the application in that Fourier domain. Similarly, one compression technique, you can see this one general image you see here. Without compression, you require suppose 1.4 per megabyte. Now after that JPEG JPG format, suppose compression. These are the compression technique. Now this is now 1.4 MB, sorry, bytes to, and that is reduced to 89 kilobytes. Okay. And ratio, compression ratio is 16:1. That means earlier whatever that is, that's what compression is happened. So idea is here what happened in this process. That's why if you see that there are so many format, TIFF format, JPG, PNG, because different format, different compressor ratios are there. So that's why general concept is always we are using JPG image, because that is compression everything with respect to good. So, but otherwise you can use also other format, but all things are compression technique. And also whenever you can think any image, you are just copying here to there, and so many times you will do, obviously that will degraded will happen. So you will not get that originality. And so these are the idea I can say. Similarly, movie also the similar way compression technique is used, and few MATLAB command you can see whatever the things I did. 3 commands you can use. I am read, I am show, and color map, I am write. These are the command you can use. Subsampling. If you know the MATLAB, any question you can ask, and also anything suppose you want to further, please you can ask me. This email ID mine, my mobile number and office number is there. I can stop here, sir.
Thank you, Dr. Pradhan,
Yes, sir.
for your nice representation and your speech taught new sites from current researchers. Please accept our thanks for your great presentation. Thank you, sir. Now we start questionnaire session. It is the time for questionnaire session. If participants have any question, send it in chat box. First question to Sridhar sir. Can we model to any problem? Sridhar sir, a question for you. Can we model to any problem?
Any problem is related to what?
The question is climatic.
Any climate problem?
Yes, sir.
But the problem that should be known. There are a lot of problems related to climate, but the problem, any problem, if you tell, if it is related to climate, then obviously we can model, but not by everything, cannot be by the regional climate model or global climate model we are using. But obviously, if it is, sometimes I can tell some assessment problems. You know, the assessment problems means how much what is the, suppose you will ask for example, you want to assess the kind of how much disaster in terms of quantity, like money or something like that. That model cannot do this, but this is for this purpose we need some other analytical models or mathematical models. But yes, obviously we can model if it is related to climate.
Thank you, sir. Question for Devasis sir.
Yes, sir.
Can image processing be done at 4-dimensional point of view?
Okay.
Devasis sir, can image processing be done at 4-dimensional point of view?
But see, then in that case, what you need to do, each component you have to do. That means each dimension you have to do that processing independently. See, like this color image, whenever you are doing color image, what happened? In that time, each component, that means red component, green component, blue component, individual component you are processing and you are enhancing. The similar way, each component you need to do. Otherwise, there is no such method is directly is not there.
Okay. Any questions from any participant? No. Thank you again, Sridhar sir and Devasis sir, for answering these questions, for your nice presentation. It was a pleasure to have you with us. Now we have reached at the end of the 2 days webinar. Last vote of thanks.
Thank you very much. Thank you, everyone.
Esteemed patron of webinar, our loving principal, Professor Dr. Umesh Chandra Pati sir, revered resource person, Dr. Sridhar Naik sir, Dr. Devasis Pradhan sir, respected our HOD Madam, Dr. Sangeeta Mishra, members of organizing committee, all learned participants, including academicians, researchers, and students. I deem it a privilege to execute the final formality of this webinar, that is offer to vote of thanks. At the outset, I extend my heartfelt thanks to our revered principal cum patron of this webinar, Professor Dr. Umesh Chandra Pati sir, for his inspiration and excellent support to conduct such type of international webinar. Thank you, sir. From my core of heart, I extend my sincere thanks to both of our resource persons, Professor Dr. Sridhar Naik sir and Professor Dr. Devasis Pradhan sir. I am thankful to both the resource persons for accepting our invitation. I am deeply impressed by the valuable and enlightening deliberation of both the resource person on their topic. I hope their talk will be beneficial for all research scholars. Our HOD Madam, Dr. Sangeeta Mishra, for her moral support and guidance to organize such type of e-meeting. Thank you, Madam. I also wish to express my gratitude to our members of organizing committee, Alok Sir, Rajendra Sir, and web designer Satya Babu, making this webinar interesting and meaningful. Last but not least, I thank all the participants who are gathered here on e-platform by our request and for their support, cooperation, hearing patiently for 2 days and making this webinar a grand success. Once again, I thank all of you for your cordial cooperation for 2 days and makes this webinar a huge success. Bande Utkal Janani. The positive responses to this webinar are a reflection of acceptance and credibility within the educational institution. Once again, thank you for making this webinar successful, and we appreciate your continued support. Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir. Namaste. Feedback link is given.
Sir.
Chat box.
Good job
given
done.
in chat box.
टिके लेंथी है ना टिके शॉर्टकट हेतिले बेटर हेतांता बहुत बढ़िया है जी
हाँ मो सर एक्चुअली भाबुतली सब जिंसडा को माने माने पार्शियल डिपेंडेंट हां सेत भाई हां से हां
बाय
सब बुझेगा डिफिकल्ट सर
लिंक कर दिया निकल रहा ये दिया ही नहीं